So, how do you identify if a compound is aromatic or at least has aromatic components to it? Well, again, you've got your three conditions. First is that you need a conjugated system. So, well, first and easiest condition is that you need a ring. So if you're looking at a compound that's linear, it's definitely not aromatic, but if you do see rings, you're going to focus on the rings. The second is that you need to make sure that the pi systems and the p orbitals are all adjacent to one another. And then lastly, you need to make sure that you meet this 4n plus 2 rule. So the 4n plus 2 rule and the p and the pi orbitals being conjugated can get a little gray area. So let's look at 5 examples. So the first row here is cyclopentadiene. So CP is usually how it's typically abbreviated. Now, we don't have to use a p orbital, but we definitely have to use a pi orbital. So in every single of the examples you've gotten up here, we're going to consider all the pi bonds when we start looking at whether or not the system is aromatic. Now, if you look at cyclopentadiene, just without a charge, what we see is that we have pi orbital here, and we start highlighting the carbons that are involved with it, we got a gap. So because we don't have this top carbon to interact with the other pi's, there's no available orbitals because that's an sp3 hybridized carbon, that inherently is not an aromatic compound. So why would these two stand a chance? Well, when we have a lone pair, in the case of carbanion, or we are missing electrons altogether in the case of carbocation, we have a p orbital available for us to bond. So in this case, we have our pi electrons, our carbons associated with a pi, and then we can invoke these carbons as well. Because they are not sp3 hybridized, they are sp2 or sp, we do have that option of using that p orbital that's either vacant for the carbocation or holding electrons for the carbanion to incorporate into our aromatic system. So in this case, we do actually have a way to make these systems aromatic. Are they aromatic? And this is where our 4n plus 2 rule is going to come from. So to determine the number of electrons, first count up the number of pi bonds and multiply by 2 because there's 2 electrons in each pi bond. So for our pi bonds, for each of them, we've got 4. Now, if we're going to use a p orbital in order to participate in bonding or participate in the aromatic system, we have to include the electrons that are being used in that. Here we have 2, so this gives us a total of 6, which is 4n plus 2 if n is 1. Here, our p orbital doesn't have anything in it, so we get 4, which is not related to 4n plus 2. So this is your anti-aromatic compound. It ends up having electrons that are unpaired or probably actually in non-bonding orbitals that don't do anything. Now, less obvious examples. Tetrahydrofuran, I think, and that's definitely not pyridine. So, again, if we look at these systems, these heterocyclates containing nitrogen and oxygen, in terms of their pi bonds, each one has 4 electrons because they have 2 pi bonds. Now, like our previous example, the cyclopentadiene, we don't necessarily have the right groups here on these atoms. But nitrogen and oxygen both contain lone pair electrons. So if we have a heterocyclic molecule, so a ring containing something other than carbon, and it has nitrogen, oxygen, or sulfur, anything containing a lone pair has the ability to use one of its lone pairs to participate in the aromaticity of the molecule, if it does become aromatic. Now, that said, it has to use one, because you have to have a way to get those electrons onto the hetero atom. If they're not participating in the aromatic system, you inherently don't have a ring, so they're not inherently not aromatic. Now, we can only use one p orbital, and the reason we use only one lone pair, and the reason we can only use one pair is that these lone pairs are effectively at 90 degrees to one another. So nitrogen's pretty easy; it's only got one lone pair, but oxygen here has 2. And we couldn't take both of those lone pairs because they're at those p orbitals holding them are at 90 degrees to one another. So they don't really have the ability to turn and participate in the aromatic system. So if we use the p electrons, or the lone pairs, on nitrogen, we get 6, which is our 4n plus 2. And we look for oxygen, if we use one of our lone pairs, we get 6, which is also 4n plus 2. Now, this does have an implication. Nitrogen here only has one lone pair, and typically this lone pair is how nitrogen acts like a Lewis base. Well, if it's participating in the aromatic ring, it can't participate in acid-base reactions. So a compound like this, nitrogen is actually not very basic at all, because the lone pair is still being occupied by the aromatic ring. In the case of this compound, only one lone pair of oxygens is being occupied, so this oxygen still has the ability to act as a Lewis base. Now, let's say we did something a bit more complicated. Is this compound with the two oxygens in it aromatic? Well, is it a ring? Yes. Do all the atoms participate? Do we have a conjugated system? Well, if we use a lone pair on each of the oxygens, yes. We end up getting that this p orbital and this lone pair and this lone pair can participate in the ring. How many electrons do I have? Well, I've got, for my pi, I've got 4, and from each oxygen, I've got 2, which would give me 8, which is not 4n plus 2. So a compound like this would actually be not anti-aromatic. What about another example for you? Pyridine. Well, nitrogen here has a double bond, and if we count the number of pi electrons, we've got 6. If we don't use the lone pair of nitrogen, because just because we have it doesn't mean we need to use it, we get a 4n plus 2. So this compound pyridine here is actually aromatic, and the lone pairs here, because we don't need them to create a bond with the aromatic ring, end up being actually really good electrons for doing Lewis acid-base chemistry. So hopefully that helped you out in terms of identifying what's an aromatic compound and what's not. Big things. 1, is it a loop? 2, can you create a conjugated system of p orbitals or lone pairs or pi bonds using the atoms involved in the ring? If no, it's not aromatic. If yes, then you need to use the 4n plus 2 rule. If you can get the 4n plus 2 rule to work out, then yes, you in fact have an aromatic compound.